So today we're going to take a look at 3.3, which is the factor theorem. There's a couple other theorems that tie in with it we'll learn as we go. Okay, so a couple ideas to just recall that we've talked about before. What is a zero or a root? So the idea of a zero or a root is it's a value for x that if you plug it into the equation, you get 0 for y. Okay, so a 0 or a root, it's an x value. That when you plug it in, you get 0 for y. We'll learn a couple other equivalent ways to talk about roots. We could also say it's an x-intercept. Okay, we've said that before. But there's a few others we'll mention today as well. Okay, we're going to end up using long division to find roots of polynomials. So if you've done long division of polynomials from algebra, probably would be an algebra 2 thing. We're going to look at that a little bit. And let's start with an example with numbers, okay, just to kind of illustrate the concept we're going to do. And I think if we do it with numbers, then it'll make more sense when we do it with polynomials. So suppose I wanted you to factor something. Okay, in this case, something simple, the number 12. And I told you that 3 is a factor. What could you do with the 3 and the 12 to somehow find another factor? Yeah, Marina? Yeah, you take 12, divide by 3. And what are we hoping for in terms of a remainder here? Well, since I told you 3 is a factor, it has to go into 12. How would you say that? Or you could tell me what you think the remainder would be.
The remainder would be 0.
Yeah, the remainder would be 0. It has to go in evenly, okay, with no remainder. All right, so if I tell you 3 is a factor, you know 3 times something gives you 12. So you take 12, you divide by 3, and that gives you the other factor. Okay, you can do exactly the same thing with a polynomial. If I give you a polynomial and I say x minus 5 is a factor, well, you can divide that polynomial by x minus 5, and you can find the other factor. It's exactly the same idea as we just did with numbers. Okay, the goal is you're hoping for a remainder of 0. And we'll talk about this a little bit more formally later on. But if you divide something and you don't get a remainder of 0, then it's not a factor. Okay, so if I said to take 12, divide by 5, you get remainder 2. 5 is not a factor of 12. Okay. So that's the idea I just said. If you divide a by b, and you get a remainder of 0, then you know b is a factor. Okay, the reason why we're going to be doing factoring is because if you have a polynomial that's not factored, it's pretty difficult algebraically to find the roots. But if you can factor a polynomial so it's something like x minus 2 times x plus 4 equals 0, okay, it's an example of a quadratic factored. It's very easy to figure out the two values here that make this quadratic equation 0, 2 and negative 4. If that wasn't factored, it might not be as easy to see. Okay, so what I'm going to do is give you the kind of the process for dividing polynomials. It's relatively wordy when you write it out. It's easier to just do it. But I will give you the description in words first. But wait till we do an example before you ask too many questions about it. Sylvia?
I was going to ask if you can go up
The first thing when you're dividing polynomials, if your dividend is missing a term, you need to fill in a 0 for that term. If you don't, you're not going to have nice columns to line things up in. Okay? So if your highest degree term, let's say, is an x to the 4th power, you need to have every power below that. X cubed, x squared, x, and the constant. If you're missing one, fill in a 0 for the one you're missing. So that's before we even start the problem, just setting it up. Okay, step 2. You're going to divide the first term of the divisor into the first term of the dividend. Divisor is the thing on the outside, dividend is the thing on the inside when you do long division. And again, we're going to do probably 2, maybe even 3 examples of this. Okay, step 3. I'll give people a second to copy down. So this should say multiply your answer from, it's actually the second step. So after you do step 2, you're going to have an answer on top of your division symbol. Then you're going to multiply that answer by each term in the divisor. And you're going to put the result under the appropriate term. This is where if you didn't fill in zeros for the terms you were missing, you're not going to be able to line up like terms. That's why we had to do that. Okay, once we do that, step 4 is going to be to subtract the columns from, let's see, that's actually going to be from step 3. And basically, you repeat that. So then you bring down your next term, just like you do with long division with numbers, and you keep repeating this process until you either end up with a remainder of 0, in which case you're done, or the degree of the remainder is less than the degree of the divisor. Okay, so those are all the steps for doing long division with polynomials. Now we'll try a couple examples. Any questions in general on the steps before we do an example? Okay. Let's start out with this one. So x minus 3 is my divisor, and I'm dividing it into my dividend, which is x cubed minus 8x plus 3. Okay, based on the steps, what's the first thing I should do here? Before I even really start to do mathematics, I just need to set this problem up a little bit better. Yep?
Check to see if anything's missing.
Yeah, I got to check and see if we're missing any terms. We have a cubic term, meaning we have to have every power below that represented in the dividend. Okay? Do I have that in this case, Brandon? No. What term am I missing? We're missing the x squared term. If we don't have that, we're going to have trouble lining up like terms. So what should I fill in for the x squared term?
0.
Yeah. So we're going to have x minus 3 divided into x cubed. Oops, x cubed plus 0x squared minus 8x. That's good. We get the linear term, and we have the constant. Okay. Now we're ready to divide it. Let's go back and look at our step. Okay, step 2, divide the first term of the divisor into the first term of the dividend. This is the first term of the divisor. That's the first term of the dividend. So we're going to take x and divide it into x cubed. Okay, so what would you get if you did x cubed divided by x? Yeah? X squared. So that's going to go up top. Next step, multiply your answer from step 2 by each term in the divisor and put the result under the appropriate term. So we're going to do x squared times x. That's x cubed. Okay, Andrew, what's x squared times negative 3?
Negative 3x.
Close.
Negative 3x squared.
Yep, negative 3x squared. And that's it for that step. Okay, next step. Subtract the columns from step 3. And this is where some people make a mistake. When you're subtracting both terms. Subtracting everything from what's above it. So we have x cubed minus x cubed. These should always cancel out. Okay? If you've done this step right, x cubed minus x cubed, that's gone. What's 0x squared minus 3x squared? Sylvia? What's 0x squared minus negative 3x squared? Not quite. That's the mistake I see a lot. Not negative 3x squared. It's 0 minus 3x squared. What's 0 minus 3? No, when you subtract two negatives, it makes a positive. Okay, so it's going to be positive. So 0 minus 3x squared is positive 3x squared. Okay? All right, so now we've got that. And now step 5, repeat it until we either don't end up with a remainder or the degree of our remainder is less than the degree of the divisor. Right now, the degree of what I have here is power of 2. The degree of the divisor is a power 1. Okay, so I need to keep going. So bring down my next term. Okay, and repeat. Okay, Justin, if we divide 3x squared by x, what do we get?
3x.
Yep, 3x. Now we're going to take that term, 3x, and multiply it by the divisor. So 3x times x is 3x squared. And 3x times negative 3. Carly, what will that come out to? Very good. And we're going to subtract. I put it in parentheses so I don't forget that I'm subtracting both of them. 3x squared minus 3x squared cancels out. Negative 8x minus 9x. Cassie, what would that be?
X.
Yeah, that's a negative 8x plus 9x, which is just x. Okay, now my degree of what I have here, the remainder, is equal to the divisor. We need to keep going. Okay, we keep going until it's less or comes out to 0. Okay, so now we're going to divide x into x. Don't forget to bring down your 3. Okay, how about Sam? We divide x by x, what do we get? 1. Distribute your 1 back out. 1 times x is x. And 1 times negative 3 is negative 3. And we're subtracting. And if you're following along in the book, they had a slightly different problem. They had a minus 3 at the very end. The only thing that would affect nothing up until right now, is we would have gotten a remainder 0 here. Instead, because I did this problem a little differently, you're going to get 3 minus 3, or 3 plus 3, comes out to 6. Okay, so in this case, we do get a remainder of 6. Okay, so the quotient, okay, if they ask you to write it, you can write your quotient. It's x squared plus 3x plus 1. And your remainder is 6. Okay, any question on that problem? So what that means here is x minus 3 is not a factor of x cubed minus 8x plus 3. Had I done the problem in the book, which was x cubed minus 8x minus 3, then x minus 3 would have been a factor, because we would have gotten remainder 0. Okay. No, Andrew, question?
But in it, why couldn't you just, instead of doing plus 1 for the last step, why couldn't you just do minus 1 and then
minus? Well, because it's x divided by x. So x divided by x, that's a positive divided by a positive, which is a positive. Yeah. I think they were intending this problem to have a remainder of 0, but I changed it slightly. but we did it correctly. Okay, let's try this one. Okay, this time you were missing a couple terms. I've already filled them in for you. So you have your x to the fourth, x cubed, x squared, x, and the constant. Okay, anyone think they can tell me what the first step is here? Yeah?
So, 2x to the fourth divided by 2x squared.
Yeah, there's
then
your
it'd
first
be
term there.
x squared.
Your first term there. Okay, you can go ahead.
It'd be end up being x squared.
Let's see. So we divide them. Quick way to check it is multiply it back out. If you don't get what you had for the first term of the dividend, then we did something wrong. X squared times x squared is 2x to the fourth. Perfect. Okay, and we keep going. Multiply it out. X squared times x, that's x cubed. And x squared times 1 is x squared. We're going to subtract that. 2x to the fourth minus 2x to the fourth will cancel. Okay, Josh, what's negative x cubed minus x cubed?
Minus x cubed, would that be 2 and negative 2x cubed? Or just, no, negative 2x cubed.
Negative 2x cubed, yep.
Please excuse this interruption.
Okay, so yeah, that's good. Negative x cubed minus x cubed, that's negative 2x cubed. Then we have 0x squared minus x squared. Well, in that case, it's just minus x squared.
Why is it just minus x squared? Why wouldn't it be 0?
Well, because it's 0 take away 1. Think of it that way.
Oh, all right.
Yeah, so, and then it's an x squared. So 0x squared take away 1x squared is negative 1x squared. You can put the 1 in front if you want. Okay, and now we bring down our next term. And we do it again. Okay, so we take negative 2x cubed and divide by 2x squared. Okay. Orlando, what would that be?
The x.
Close. Think about you dividing a negative by a positive.
Oh, wait, negative x.
Negative x. Let's check it. Negative x times positive 2x squared is negative 2x cubed. Negative x times positive x is a negative x squared. And negative x times positive 1 is negative x. And we're subtracting all of that. First two terms cancel out. Negative 2x squared plus 2x squared. That's gone. The next one also cancels out. You have negative x squared plus x squared. So that's gone. Then you have 0x minus x. Okay, Shannon, what's 0 minus x? Just x. And bring down my last term. Well, in this case, look at the degree of my remainder. If this is a degree 1, my divisor is a degree 2. I'm done. Okay? X squared does not divide into x. Okay? So this is my remainder, x minus 2. Okay, so to write our answer, quotient is x squared minus x. The remainder is x minus 2. Hey, any question on that?
So x squared minus x. So you're basically saying 2x squared plus x plus 1 is not a factor of 2x to the fourth.
Yeah, this is in this case, the divisor is not a factor of the dividend because it didn't go in evenly.
Okay, so
We haven't done any with a remainder 0 yet. The last one should have been, but I changed it slightly. So yep. No, that's not a factor. So if we were trying to factor it, this wouldn't help us. It's not a factor. Okay, sometimes you also see your answer written, let me show it to you with numbers first. You took 10 divided by 3. Okay, if you do this out, your quotient is 3. Or actually, you know what? Let me do one where it doesn't come out the same. Let's do 13. In this case, your quotient is 4, and your remainder is how much? 1. This is how we've been writing our answers, quotient, remainder. Sometimes you also see it written like this. The answer is 4 plus your remainder divided by your divisor. 4 plus 1/3, or 4 and 1/3. So this is your quotient, your remainder, over your divisor. We could do the same thing here. So we could say it's our quotient plus our remainder over our divisor, 2x squared plus x plus 1. It's exactly the same thing we just did with numbers, except it's with polynomials. Any question on that? If they ask you to write it this way instead? If you get confused, just go back to numbers. Think of it that way. And instead of 4, 1, and 3 being numbers, they're all polynomials now. So if we have two polynomials, which I'm going to call f of x and h of x, then, and they can be any polynomials you want, as long as you're not ever dividing by 0, then there always exists two other polynomials, q of x and r of x, which are calling the quotient, that's q of x, and r of x is the remainder, such that this is true. And I'll show you an example here with numbers. Let's pretend let's use the example we just had. 13 and 3. 13 and 3. Okay, so what I'm saying here is that I can write 13 as 3 times my quotient. In this case, the quotient would be 4. 3 goes into 13 4 times, plus my remainder, which was 1. 13 equals 3 times 4 plus 1. So this is the same concept I'm trying to show you right here, just using numbers instead of polynomials. Okay, any question on that idea? Okay. Okay, remember that the degree of your remainder is always less than the degree of the divisor, or you could end up getting a remainder of 0. So if we divide by a linear polynomial, okay, something kind of like we did in the first problem, we divided by something linear. If I'm telling you that the degree of your remainder is always less than the degree of your divisor, what happens? What's 1 degree less than being linear? What does it become if it's 1 step below linear? Yeah?
Wouldn't it just be a number?
Yeah, it would just be a number. So anytime you divide by a linear polynomial, the degree below that is a constant. Your remainder is always a constant. Just a number. So an example of a linear polynomial, x minus 2, x plus 5, y plus 7. Okay, those are linear polynomials. So here's the same concept, just written out as an equation. So if you take a polynomial, f of x, and you divide by something linear, x minus a number. And it could be x plus a number, just pretend c is negative. Okay? So if you divide by something linear, using what we had up above, I'm rewriting that more specifically this time when your h of x is a linear function. Not just any function, but it's something linear. So simpler. So f of x would equal what you divided by times your quotient plus your remainder. But in this case, we know the remainder would be a constant. Any questions on how we got this equation? F of x is your quotient times what you divided by plus your remainder. Okay, basic, that's how you check your answer when you do division. See if you got it right. Okay, now let's look at what happens if x equals c. I want to focus on what would happen in this equation on the right-hand side. So I want to basically look at f of c. Okay, not f of x, but f of c. What would happen in this first term right here, where I have x minus c? If x and c are the same, what is that going to become?
0.
Yeah, it's going to become 0. Because you're going to change, we're just going to change x to c, and I'll show you why in a second. So you end up with c minus c times your quotient, which is q of, we're finding a particular value, c, plus my remainder. So what happens is this whole part right here goes away. And what's the only thing you're left with? A remainder. So this is actually a neat little formula. It gives you a way to find the remainder without actually having to do long division. Won't give you the quotient, but it will give you the remainder. Okay? So if you want to know, we're going to call this the remainder theorem. If you want to know what the remainder is, and you're dividing by something linear, okay, this only works for linear. It doesn't work for anything else. At least what we're studying. Okay, if you divide by something linear and you want to know the remainder, just plug c into the original function, and that's your remainder. And the reason why is because this whole part right here disappears. And all you're left with is r. So if you want to know your remainder, just fill c into the original function, and it will equal the remainder. So it's a little shortcut to find the remainder. Okay, so where that would come in handy is I may give you an insanely long numerator. Okay, and all I ask you to do is find the say, remainder when you divide by x minus 2. Okay, well, that wouldn't be bad to do if you use the remainder theorem. But doing out the long division might be extremely hard. Okay, so if I only want a remainder, keep this theorem in mind. Plug in the value after the minus sign. Okay, does everyone have the remainder theorem? All right, so this isn't that bad. We could do this long division out, but let's use the remainder theorem. For example 3, I just want to know the remainder when you divide f of x by h of x, and then when you divide f of x by g of x. So let's start out with the remainder for f of x over h of x. Okay, to get that remainder, all I have to do is plug a certain number into function f. What number would I plug in to find the remainder for f of x over h of x? Nick? Want to help him out? What is the remainder? Brian, what does that remainder theorem say? Plug in.
You have to plug in the two, 5.
Plug in what?
You have to plug in the 2 polynomials. 35.
Well, you're plugging a single number, right? So we're not plugging in a polynomial. We're just plugging in a number. Okay, what number would you plug in to find this, Josh?
-3.
Well, let's go back. You're close, but it just says if you want to divide by x minus c, you find f of c. So whatever c is. C is what's after the minus sign. So in this case, we'd plug in 3. So let's plug 3 in, see what we get. We get 3 cubed minus 2 times 3 squared plus 3 minus 5. So 3 cubed is going to give me 27. Minus 3 squared is 9 times 2 is 18. Plus 3 minus 5. Okay, Taylor, what's 27 minus 18? 9, yep. So 9 plus 3 minus 5. Okay, and Julia, what's 9 plus 3? 12, and take away 5? 7. So that would be the remainder. So if you were to do out this long division, that's the remainder you would get because of the remainder theorem. Okay, let's try the remainder for f of x divided by g of x. Okay, what am I going to plug in this time? Cassie?
-1.
Yeah, -1. Okay, it's what comes after the minus sign. If you want to rewrite g of x, think of it this way. Circle what comes after the minus sign. -1. That's the biggest mistake people make when they use the remainder theorem, whether it's a negative or a positive. All right, so we have -1 cubed minus 2 times -1 squared minus 1 minus 5. Okay, so -1 cubed, that's still -1. -1 squared is +1 times -2. Okay, and now just do your subtraction left to right. So -1 minus 2 gives me how much? -3, take away 1 more. -4, and then take away 5 more. Here's your remainder. A lot easier than doing out the long division if you only want the remainder. If you want the quotient, well, you got to do out the long division. Any question on how to use the remainder theorem? Yes?
Can you go back to it?
Back to the remainder theorem? Yep. So this is kind of up above. This is the explanation why. Okay, if you fill in C, we saw that the first part I had here cancels out, and you get your remainder equals the value of your function at C. So it's a nice little formula to find the remainder. But this is the general idea. Okay, and it only works when you divide by something linear. So it's a nice shortcut, but it's also pretty restrictive. It doesn't work all the time unless you're using linear. Okay, any other questions on that? All right, so using our remainder theorem, it's basically what we just had on the other page again. F of x would equal our quotient times our divisor plus f of c. But what does f of c really give you? It's the remainder. I just didn't write as a remainder this time. I wrote f of c. Okay, but when you plug in c into your function because of the remainder theorem, that's a remainder. Okay, let's suppose that c was a root. Let's suppose that c was a root. Okay, what that means is if you plug c into function f, you get 0 for y. That's what it means for something to be a root. So let's apply that idea to the remainder theorem. Okay. So f of x would equal our quotient times our divisor plus our remainder. But in this case, if the remainder is 0, it's just plus 0. And what that means is it's a factor. Okay? That's the important point here. Notice it's written as f of x equals something times something. Whenever you write it that way, 12 equals something times something. And there's no remainder here. Both the 3 and the 4 are factors. Okay? So that's where the remainder theorem is going to help us out. If we get a remainder of 0, we just found a factor. Okay, and our factor theorem, formally it says that let f of x be any polynomial. Then x minus c will be a factor if and only if c is a root, or c is a 0. The reason why? If it's a root, we're going to get remainder 0. So now we have another way of saying a couple statements I said earlier. If something's a root, it's a 0, it's an x-intercept, and x minus c is a factor. That's a fourth way of saying the same thing. So if I said to you 5 is a root of this polynomial, then x minus 5 is a factor of it. I could also say 5 is an x-intercept. Or I could say the graph crosses the x-axis at 5. I'm saying the same thing, many different ways. Okay, so we're going to use the factor theorem to show that x plus 2 is a factor of x cubed plus 5x squared plus 5x minus 2. Okay, and if it confuses you to think of it as the factor theorem, just think of it as the remainder theorem. You're going to find the remainder when you divide by x plus 2, and you're going to hope that the remainder comes out to 0. If it doesn't, then x plus 2 is not a factor. Okay, so what number would we plug into, let's call this whole thing f of x? What number are we going to plug into f of x to check the remainder when we divide by x plus 2? Yep, Josh? Negative 2. And what are we hoping it comes out to? We're hoping for 0. If we get 0, then we proved that's a factor. Let's try it. So now we have negative 2 times, so negative 2 cubed plus 5 times negative 2 squared plus 5 times negative 2 minus 2. Let's see what we got. Negative 2 cubed is negative 8. Negative 2 squared is 4 times 5 is 20. 5 times negative 2 is negative 10 minus 2. Negative 8 plus 20 is 12. And then 12 take away 10 is 2. And 2 take away 2 is 0. So, if we divide that polynomial by x plus 2, we get remainder 0, which means it's a factor. Any question how we just proved that it's a factor without doing long division? Okay, so this would be the first step. If we wanted to factor this, x cubed plus 5x squared plus 5x minus 2. Okay, I I know one of the factors is x plus 2. How would I get the other factor? X plus 2 times, well, this thing would be pretty easy to figure out. We learned how to do it, yeah?
Divide the left side by x plus 2.
Yeah. We divide the left side by x plus 2 and do the long division out. This would be your quotient. Whatever you get for a quotient, and there'd be no remainder, we already know that, that would be the other factor. So now that's one way you can factor a cubic equation. You might have not known how to do it before, but if you can find one root, then you can also find a factor. Okay. I'm not going to do this out. That's not the point for today. Okay. Any question on that?
So you find one factor, you can find the other?
Generally, if it's the kind of problems I'm going to give you, yes, because I'm going to make the factors nice, generally integers or rational numbers. If they were imaginary, that's another thing we'd have to look at. But in general, once we can take something down from being a cubic and make it a linear times a quadratic, we're good. Because we have formulas for solving quadratics, which is what this quotient would be. It would be a quadratic quotient. Okay? The problem is when we have things that are higher than quadratics, we don't have formulas for them. Okay? And we don't know how to factor cubics nicely. So we got to take them down one step at a time. And all the problems I give you will, when we start doing that, they will work out nicely. So there'll be special ones that you can actually do. Okay, so here's some equivalent statements about roots and zeros. Okay, we've said all of these before. We're just going to put them all together in one list. Suppose that c is a root. Okay, what that means is that if you plug it in to the function f, you're going to get 0. That's what a root is. You plug it in, you get 0 for y. I just said that one. So c is a 0 of the function. C is a root of the function. Same thing. This is the new one. If c is a root, x minus c is a factor. And that's what we just did on the last problem. So I think we showed that, what was it, -2? Yeah, -2 was a root. So x minus -2 is a factor. And generally, we don't say x minus -2. We change it to x plus 2. And we could also say that c is an x-intercept on the graph. Okay, all of these statements are equivalent. Any questions about any of those statements or what they mean? Yep?
And how do you find if c is a root again?
How do you find if c is a root? You're going to check if x minus c is a factor. And how do you check if something's a factor? We divide it and we check for what? Remainder of 0. Yep. So if I ask you to say, is 2 a root of this equation? Check this. Check if x minus 2 is a factor. How do you check it? See if you get remainder 0.
So basically, you're looking for remainder 0. If there's a remainder 0, then c is a root.
Yep. Yep.
So being a root and a factor is the same.
Right. Being a root and a factor is a very similar idea. You just have to say it a little differently. If 5 is a root, you wouldn't say 5 is a factor. If 5 is a root, x minus 5 is a factor. Yep. Okay, here's one that's a little bit different. I'm giving you all the answers, and I want to know what the original polynomial would be that has those 3 roots. And I specifically want the coefficients to be real. You could do this with imaginary numbers, but I don't want to. Okay, so keep in mind what I just said. If -2 is a root, then what else must be true?
And wouldn't 1 and 3 also be roots?
Yep, 1 and 3 are roots. Yep. But what's another way of saying -2 is a root? Yeah?
X plus 2 is a factor.
X plus 2 is a factor, yes. Negative 2 is a root, x plus 2 is a factor. Okay, how about someone else? If 1 is a root, then what's another way of saying that? Taylor?
X minus 1 is a factor.
X minus 1 is a factor. Yep. And lastly, if 3 is a root, x minus 3 is a factor. That would be my polynomial. Now, if they wanted us to FOIL this out, that's just an exercise in Algebra 1. I'm just going to leave the answer like that. That's my polynomial. X plus 2 times x minus 1 times x minus 3. Okay, let me see if the, the book actually does have it all FOILed out. It comes out to x cubed minus 2x squared minus 5x plus 6. If you FOIL it out. Okay, any question on that idea? We're going to come back to this idea when we do complex numbers as well. When I say find a polynomial that has complex roots of, say, 1 plus I and 1 minus I. It's going to be the same idea, except with complex instead of just real numbers. But that's how you do that. Okay, now what if I did this? Let's say we had x plus 2, x minus 1, x minus 3, and x minus 3. I added in one more factor. What are the roots of this equation?
Negative 2, 1, negative 3.
Negative 2, 1, and what's the last one? 3. Okay. They are the same roots as the other equation. What's the difference, though? These two equations would have exactly the same roots, these two polynomials. But what would be the difference with this one? Yeah? This would have a degree of 4. Very good. It would have a degree of 4. I specifically asked for a polynomial of degree 3. So if I asked you for a polynomial of degree 4 with those roots, well, then you've got a lot more options. You just have to repeat one of the roots somewhere. Okay? This would look more like a W shape. The one up above would have the cubic behavior where each end goes positive and negative infinity. All right, so let's try to find the zeros of this cubic equation. Okay, this time I don't think you're going to need to use long division or the remainder theorem. I think we can use factor by grouping. Okay, so factor by grouping is when you group the first two terms and the last two terms so that they have something in common. Okay, that's the way the book had it written, so I'm writing it the same way. And let's pull what we can out of the first two. Okay, what do the first two terms both have in common? Cassie?
X squared.
Yeah, so let's take that out. What does that leave you with?
X plus 2.
Yep, x plus 2. Now the goal with factor by grouping is you're hoping to get x plus 2 again. Because then if you get it again, you can factor that out. Okay? So let's check the second set of parentheses. Okay, what can we factor out of there? Second set, Josh?
Negative 4.
Yep, let's factor out a negative 4. And what would that leave me with?
X plus 2.
X plus 2. Yep. Negative 4 times x is negative 4x. Negative 4 times 2 is negative 8. Okay, and now we have the same factor repeated. So let's factor that out. Okay, so we have an x plus 2. And what would that leave me with if I take x plus 2 away from the first term? All I have left there, Tahina? Yeah, so the first term would be x squared minus 4. And the second term would be, first term is just x squared. Second term is the minus 4. Okay, you cannot do this with all cubic equations. This one I picked special numbers to make that happen. Okay, but any question on the factor by grouping? That's what that's called. All right, now we can we can solve it because it's fully factored. So Andrew, what do I know must be true if I'm multiplying something times something and I'm getting 0 as the answer?
You're going to get a positive and negative result.
How can that happen if you multiply two things together and get 0? Like if you had to explain that to somebody like really little and they just said, well, what has to happen to multiply two numbers together and always get 0?
0 has to be in there.
0 has to be one of the factors. Yeah. So either x plus 2 is 0, or x squared minus 4 equals 0. Okay, and now we solve each one. Okay, so the zeros here would be negative 2. And actually, technically, we should write and. So negative 2. And how would I solve that other equation? X squared plus 4 equals 0. Yep.
You'd add 4 to each side and then root over 4, which is 2.
So x would equal, what would it be from here?
2 or negative 1?
Yeah, you get 2. And negative 2 is also the answer. But we already have negative 2 from the other equation. So what's happening, this is a cubic equation where negative 2 is a repeated root. It happens twice. You don't have to write it twice. But if you were to graph this equation, what the cubic would do is it would come down, it would touch the axis at negative 2, and it would bounce right back up. Because that's called a repeated root. Negative 2. Okay, any question on the zeros there? All right.
So your factors would be
Your factors would be x plus 2 and x squared minus 4. Yeah. I guess if you wanted, you could have factored x squared minus 4, because this is a difference of 2 squares. Or I just said, why don't we just solve it at this point? But if you were to factor x squared minus 4, that would factor into x plus 2, x minus 2. So all of your factors would be x plus 2, x plus 2, x minus 2. That's it. Any question on factoring that one step further if you wanted? You don't have to, because I think you can just solve it at that point. All right, let's look at this one. So we have the graph 2x cubed minus 4x squared plus x minus 2. Okay, and we're going to use a graphing calculator to help us out a little bit. All right, so let's type that in. Okay, so 2x cubed minus 4x squared plus x minus 2. It looks like there's a root at 2. Okay. How I could quickly check if that's a root, all I'd have to do is plug that in and see when I plug in 2 for x, do I get 0 for y? I could check that really quick. Or, in this case, I'm just going to use second calc root 0. And it confirms what we thought. There is a root when x is 2. Does it look like there's any other roots there? No. Well, we haven't learned this yet, but a cubic equation has to have 3 answers. They don't have to all be distinct, but there does have to be 3 answers. So what does that mean about the other 2? Mhm.
Would they be undefined?
No, they're not undefined, but they are answers we can't see graphically, which means something. Yeah?
Are they gonna be two?
They're going to be what?
Are they gonna be two?
Oh, you mean all be the same?
Yeah.
They're not all going to be the same. I know what you're saying. Like if you were to graph x minus 2 3 times, this would be a polynomial that has one root, but watch what it looks like. That's what a cubic polynomial looks like when it only has a repeated root 3 times, x minus 2, x minus 2, x minus 2. It looks like it never even curves back on itself. But that's a good guess. That's a good guess. Okay. Any other guess about the other 2 answers to that curve in blue? They're imaginary. Okay, they're imaginary or complex. So we can only see one real answer. The other ones have to be imaginary. All right, so in this case, directions said to find the zeros. Since we haven't studied imaginaries yet, we'll just stick with the real zeros. So x equals 2. To find the complex zeros, this would be the first step. Now you'd have to use long division, divide through by x minus 2. It would go in evenly. You'd get a quadratic, and then you'd solve it with the quadratic formula. And you'd get I in your answer. Okay, again, I'm not going to go through that today because we're not there yet. But that's your only real root, x equals 2. Okay, any questions on that? All right, so hopefully everybody feels a little bit more comfortable with using the remainder theorem and long division to help with factoring polynomials. Okay, so the homework tonight starts on page 171. And it's 1, 2, 4 through 6, 9 and 11. It's 13, 15, 17, 19 to 21, 25, 27, and 32.